Eduardo Duzzioni is going to finish his course. Thanks a lot, Eduardo, for the talks, for the lessons. Right after his talk, we will have the photo of the conference, of the school. So the photo will be here in the front of the building, of the auditorium. So we just need to go out of the auditorium, and the guy will take a picture of everybody here. Okay? Thank you very much. So after the talk, don't go for lunch immediately. Eu vou ficar aqui, Eduardo. Perguntas? Questions? I will give the microphone, right?
Hello? Are you listening? Okay. Okay. Hello, everyone. Good morning. Welcome back to our last talk about the introduction on quantum computing. I hope you are enjoying this mini course. Today I will talk about quantum computing, adiabatic quantum computing. This is a different model of quantum computing. This is time-continuous way of performing computation. And this is a very nice model, and I hope you enjoy it. Let's start from the beginning, okay? This is the Schrödinger equation. When try to solve the Schrödinger equation, if the Hamiltonian is time independent, we know that the evolution operator is quite simple, right? Although it's not always simple simulated, right? So if you expand the solution, the base state here, the initial state, if you expand it in the eigenbasis of the Hamiltonian operator, then it's possible to find this solution. This is very basic in the course of quantum mechanics. Then if you choose as initial state just one of the eigenstates of the Hamiltonian operator, then your coefficient here will be 1, and you'll find the solution. This means that the only time dependence of these states is on the phase here, while this eigenstate, it doesn't depend on time. So the solution is quite simple. Okay, but what is the difference when you try to solve the solution of the Schrödinger equation when the Hamiltonian is time dependent? That's the problem. When the Hamiltonian is time dependent, then when expand the solution of the Schrödinger equation, psi of t, as function of the Hamiltonian eigenstates, n of t now, observe the time dependence here, then it's possible to write the solution in this way. This phase is the dynamical phase of the evolution, and this is the time-dependent coefficients. So the solution of the Schrödinger equation will be determined if you find these coefficients. But the problem relies exactly here. It's possible to show, and this is the exercise you need to do, that if you replace this expression here in the Schrödinger equation, then you find this equation for the coefficients of the expansion. Observe that if you try, for instance, find the solution for the coefficient C1, observe that this coefficient depends on the other coefficient, right? 2, 3, 4, and so on. So they are coupled. That's a problem. For that reason, it's very difficult to solve this equation. But there are different strategies to approach this problem. And one of these strategies is when you consider a adiabatic evolution. Of course, there are some constraints, but it's a possible solution to this problem, right? We will see now what are these constraints. Okay, it's clear this exercise? No problem? Okay. What's the idea of adiabatic evolution? Let's see. A quantum system that begins in the non-degenerate ground state of a time-dependent Hamiltonian will remain in the instantaneous ground state, provided the Hamiltonian changes sufficiently slowly. That's the key word, sufficiently slowly. But compared to what? The adiabatic theorem that establishes this constraint. Okay, this is another exercise. This is a bit more difficult than the previous one, okay? If you follow this reference, it's a friendly paper and you can reproduce these calculations, right? This is the statement, one of the possible statements of the adiabatic theorem that guarantees that if you wait time enough, I mean, this capital T is the total time of the evolution of the system. If this capital time is much greater than this expression, here we have this transition element. Observe that this is the derivative of the Hamiltonian, right? S is defined, this is a n-dimensional parameter, T over capital T. And this quantity G and K is the gap, the energy difference between the eigenvalues En and Ek, right? So the basic idea here is, okay, I'm trying to do quantum computation by evolving the system adiabatically. How long does it take to process and find a solution to a given problem? It will take this capital time T, right? Observe that if the gap between the ground state and the first excited state is very small, your time increases. That's the problem, right? That's the problem of quantum computing through adiabatic evolution. Okay, but you can think that, okay, is this a really problem? Actually, adiabatic quantum computing, first important message is, it is a universal model of quantum computing, okay? And if you think about complexity, it's polynomially equivalent to the gate-based quantum computing model. So both models are equivalent. That is very important. That's why I said, okay, gap is the problem. No, the gap is taking into account the nature, right? Okay, this model, I think it's very interesting because it's more physical. I am a physicist, right? So I like this kind of thing. So it's at least interesting to me. Okay, think that nature is processing all time, and you can think that a physical system evolving is processing information. And if you are trying to describe a given process, you just think that nature is performing all these calculations for you. This means that computation at the end is a physical process. That is very important, right? And what's the idea of the adiabatic quantum computing? The idea is prepare a simple initial state. Then, if you evolve this state adiabatically, at the final process of the evolution, after a time capital T, we will be in the ground state of the final Hamiltonian, and this Hamiltonian contains the solution to your problem. That's the basic idea of adiabatic quantum computing. Okay, I will explain this in detail now. The time-dependent Hamiltonian of the system, in general, this is not a rule, but in general is composed by two parts. This is the initial part and this is the final one. A of t is a time-dependent parameter, real parameter like B. But the condition is that at the initial time, here, the system, the state of the system is the eigenstate of the Hamiltonian age I. So A of 0 is equal 1 and B of 0 is equal 0. And at the final of the computation, the coefficient A of t is null, and the coefficient of B of t is 1. So at the end, we have just this Hamiltonian. At the beginning, you have just this Hamiltonian, and at the end, we have just the final Hamiltonian here, HP. An important condition is that these two operators, they don't commute. It's easy to see that. Basic quantum mechanics, right? Because if these two operators, they commute, so they have the same eigenstates, right? So if they have the same eigenstates, this means that probably the solution of the initial Hamiltonian must be the same as the final Hamiltonian, and you know at the beginning the solution of the problem. So this is not useful, right? Okay, how to implement that? Okay, I didn't mention the first idea of adiabatic quantum computing was proposed by Eduardo Duzzioni at the beginning of 2000s. And the idea of Eduardo Duzzioni was to solve the three-set problem, one of the satisfiability problem that I mentioned some lectures ago. Is a NP complete problem. And in the paper, which was published in Science, they used just about 20 or 22 qubits, and the time of computation for the three-set was scaling polynomially, quadratically, so they were very happy, okay, because they were solving a very hard problem using quantum computer. But the problem that if you continue for more and more qubits, the gap closes and the time of computation increases a lot, like exponential. That was the problem. Okay, so how to encode the initial Hamiltonian? One possible idea is, okay, the Hamiltonian must be simple because I must know how to prepare the initial state in the lab, okay? In this case, a possible state is this one. This is the identity operator. Observe that the action of each of these operators inside the parentheses on each stage plus will result 0, right? So the ground state has as eigenvalue the number 0 here. The final Hamiltonian HP is called problem Hamiltonian, and as I mentioned, it encodes the solution to our problem. Another important thing in adiabatic quantum computation is to define the time independence of this coefficient, A of t and B of t. In general, we use this kind of function. There are many possibilities, infinite possibilities, but this is usual, right? I already mentioned the meaning of t and s. So, in general, people use linear interpolation, but it's possible to choose other functions. If you go, I don't know if you already used the D-wave quantum computers. Someone here had this experience? D-wave quantum computation? No? Quantum annealing? No? There, it's quite usual to implement. It's also possible to choose your scaling function that we call S of t. It's possible to choose a linear behavior of this function. Okay. Now I'm going to talk about the running time and the gap. The idea is that, okay, if I wait a long time, the capital T, the total time of the evolution, if I wait long enough time, I will be sure that I will be very close to the ground state of the system, but we don't know how long is this. Actually, this will depend on each problem. Each problem, as I mentioned, the example of three-set problem, is a very hard problem, so it will take much time. then it's necessary to analyze each case. And what really determines this capital T is the adiabatic theorem. But observe that from the practical point of view, adiabatic theorem is, in the major part of the case, unuseful. Can you see why? Opa. Here, observe that to calculate this term, it's necessary to know the eigenstates and the eigenvalues. If you already this work, you already have the solution of the problem. So, from this point of view, this is not useful. In some cases in which it's possible, for instance, in the case of a Grover's search algorithm, it's possible to use there because there we have a very high dimensional system if you have a big database, and you can translate this problem with high dimension to a two-dimensional system. Just in this case. Other case is not. This kind of problem, it's useful, but in general for real problems in real life, it's not useful. But what do the experimentalists implement in the lab is, okay, they fix an initial time for the evolution and measure the final state and compare if when they measure several times the final state, we always get the same solution. If it isn't enough, okay, you enlarge your time and measure again, again, and again until you get the time enough to implement your solution to your problem. Okay, we saw that the gap between the ground state and the first excited state is very important to determine the total evolution time, okay, and it grows with square here. There are some versions of the adiabatic theorem in which there are corrections, so sometimes it's possible to appear higher orders here, okay? Okay, this is the basic idea. But how to improve the computational time? There are different strategies. One of these strategies is to change the interpolation function, the scaling function S of t. This is possible. Change the value of the parameters that compose this function. There are other approaches in which, instead of use just two Hamiltonians, the initial and the final one, but intermediate Hamiltonians, it's also possible. And the idea is that put these intermediate Hamiltonians to avoid the close of the gap. Okay, that's the idea. And sometimes it's possible, but it's not easy to find final Hamiltonians that commute with age p, but they are much simpler of implement than the usual final Hamiltonian. Okay, this is the basic of adiabatic quantum computation. Would you like to take off your mask, please?
You could construct the HP Hamiltonian to solve in a specific problem,
Yeah.
and how you could like implement this on lab.
Yeah, of course. That's very important. It's necessary to know how to build the final Hamiltonian because it will contain the solution to your problem. That's right. I will show at the end of the presentation. Ah, okay, there are one more question there. Ah, no? Ah, okay. Ah, okay. Okay, okay. I will show an example at the end. I will show actually two examples how to build the final Hamiltonian. One is to factoring. It's possible to factor and use this kind of quantum computation. And the other example, I will show how to solve differential equations. Okay?
My question is about when we talk about adiabatic, it's for the Hamiltonian or for the state, for the evolution of the state, because the evolution must be unitary, right? And the unitary operators comes from the Hamiltonian,
Right.
but the evolution of the state is also adiabatic, or just the change in the Hamiltonian?
Okay. The evolution of the state is considered an adiabatic evolution when this state remains in the ground state of the time-dependent Hamiltonian. If this state, if there is no transition between one eigenstate to other eigenstate, we means that this evolution is adiabatic. Hamiltonian is just the control of the system, right? So the state that evolves adiabatically. Okay, it's clear? Okay, let's move to quantum annealing. The idea of quantum annealing is quite similar, although there are some differences that, and also the orange of quantum annealing is a bit different, okay? Quantum annealing is an optimization process, okay? The idea is to find, if you have a cost function and try to find a minimum of this function, you can use adiabatic quantum computation, but also quantum annealing. I will show the difference between these two processes, okay? And the idea is that in quantum annealing, you make use of quantum fluctuations, right? From the history point of view, this method, quantum annealing, is inspired on simulated annealing. Simulated annealing is based on the annealing process. The annealing process, the idea is to find an equilibrium state for very low temperatures. So the idea, okay, melting the material, understood, lowering the temperature very slowly, and spend an amount of considerable time to achieve the final state that is a very low temperature. It's something like that. Suppose that this is a constant function, and here we have local minimum, and this is the global minimum, right? So the idea is to arrive here. But there are different strategies. If you use the simulated annealing process, what do you need to do? Okay, you use the thermal fluctuations. That's the idea. With these thermal fluctuations, it will be necessary to, with this, it will be possible to jump these energy barriers, okay? But observe that it's important to jump these barriers. And if you have fluctuations enough, we will be able to arrive here, right? This is the inspiration for quantum annealing. Observe that the first paper, it was 2 years before quantum computing, right? So the motivation is different. But today, it's quite common people say that these are the same thing. I will show why. Okay, so what's the idea of quantum annealing? The idea is to replace these thermal fluctuations by quantum fluctuations, okay? So instead of jump the barriers, the idea is to tunnel through these barriers, right? That's the idea. So according to the evolution of the time, if you prepare our initial state as the ground state of a simple Hamiltonian, and you change the Hamiltonian very slowly, you observe that at the end of the evolution time, the state of the system will be in the ground state of the final Hamiltonian. That's the idea, okay? So it's necessary to change temperature fluctuations by tunnel effects, right? Okay, and there are particularly some interesting cases in which quantum annealing seems useful. The idea of D-Wave company was to develop a dedicated quantum computer able to solve NP problems. They already mentioned that, but we know that they are unable to do that, right? Even people don't know if the D-wave quantum computers are full quantum because they have a lot of decoherency, errors, and so on. But it seems that for some problems, like optimization problems, combinatorial, discrete problems in optimization, such as combinatorial optimization problems, it seems that this quantum computer is useful, but there is at the moment a proof that it's better than the classical computers, right? Okay, how do we implement the quantum annealing? Okay, the idea is when you try to solve an optimization problem, you have a cost function, and we map this cost function to the final Hamiltonian that contains the solution to our problem, its ground state. And we initially now, this is a basic difference between adiabatic quantum computing and quantum annealing, because in the quantum annealing, it's possible to initiate in arbitrary state. Okay? Observe that, as in the classical case, it's possible to start in every point, and the system will be driven to the final state. So in the quantum annealing, it's also possible to start from an initial state, from an arbitrary initial state. This is the basic difference. And other difference is that when you are thinking about adiabatic quantum computing, we think that the system is at 0 Kelvin, while in the quantum annealing case, in practice, this system is in thermal equilibrium. So this is a big difference because temperature will introduce a lot of effects, like the coherency, and the final state of the solution will be affected by that, right? In this case, I am using a different representation for the scheduling function. Observe here. AGF is the final state, and AG he is the transverse Hamiltonian. Observe that although this Hamiltonian age of t is different from the previous one of adiabatic quantum computing, let me show you. It's possible to choose A of t and B of t such that these two expressions are equal, right? This coefficient gamma of t is the transverse field coefficient. It's important. At the beginning, it's very high, and at the end of the computation, it's 0, right? And we will stay with this Hamiltonian age f, which will solve our problem. And what is the interpretation of this transverse field Hamiltonian? This term, this transverse field, this term here, it will introduce basically kinetic energy on the system, and this kinetic energy will introduce more quantum fluctuations in the system. This will enable the system to tunnel through the barriers, okay? And we hope at the end of the computation you'll find our desired solution. That's the idea. At least on the paper, it seems very nice. The ideas are very elegant, but until now, there's no proof that D-wave quantum computers in the D-wave are better than our classical quantum computers. Okay, let's see how to implement that in a D-wave system. In general, D-wave encodes the final Hamiltonian as the Ising Hamiltonian. I don't know if all of you already know this kind of Hamiltonian. It's common for you? No? This Hamiltonian, okay, H, I, and capital J, I, J here are the coefficients in these coefficients, you encode the solution to your problem. Here, you define your problem here, encoding these values of these coefficients. These are sigma z, the Pauli matrix, right? Observe that this Hamiltonian is diagonal in the computational basis. So what's the idea? The idea is to interpolate, as I mentioned before, from an initial state AGI to an initial state, this one, and this one. Observe that as this Hamiltonian is diagonal in the computational basis, this means that you just measure population, you just measure zeros and one. At the end of the computation, the state of your system will be a string of zeros and one, just that. Instead of measure a superposition state that would be necessary to perform state tomography, right? So this is important, but it is also important to note that with this Hamiltonian, this Ising Hamiltonian, it's not possible to implement all problems you desire. That's a problem, right? But quadratic Hamiltonians, a lot of problems, traveling salesman problem, etc. It's possible to implement here, right? In this case, in the D-wave system, the initial Hamiltonian is this one. So the eigenstate of this Hamiltonian, observe that is just the sum of sigma x. So the initial state, okay, it's not written here, but the initial state that is the eigenstate of this Hamiltonian is the tensor product of states plus, right? And as you know, the final Hamiltonian is the Ising Hamiltonian, and one state with this form is an eigenstate of the final Hamiltonian. This is a string of bits, right? Just to know that in the IBM, in the D-wave systems, the temperature there is 15 millikelvin, okay? What's the idea when implement this computation on the D-wave system? We will run this problem several times, 1,000, 10,000 times, it's possible to control. And every time that you run your problem and you measure and you get a given string, with this string we will obtain the value for the energy of the ground state. And at the end, what we will do, we will pick the lower energy, just that. This is the solution to your problem. Observations is that, okay, we know that we are in a noise intermediate scale quantum computer, so the coherency is important. There are other imperfections in the experiment. Another observation is that adiabatic quantum computing and quantum annealing are treated as equals, but it's not true. Okay? And that application that I mentioned, right? This is an application, how to use this kind of quantum computers to find the prime factors of a given number, right? Let me see what time is it. Okay. What's the goal of factoring? Yesterday, we saw that if you have an integer number n, this number can be written as the product of two prime numbers, p and q. So the idea is, given n, what are p and q? That's the question. That's why we wrote this problem as n minus p times q is 0. That's our idea of implementing, of mapping this factoring problem in the Hamiltonian. So our cost function is this one. Okay, what's the reason for this number 2 here? It's because I'm interested in to have a lower bound, that's 0, right? So I know that when more closer I am to the 0 here, I am closer to the final solution to the problem. That's the idea. Otherwise, if I don't have this square here, it would be possible to have negative values, and negative values can go to minus infinity, for instance. That's a problem. So our idea is to find the values x and y such that x is equal p and y is equal q. This is our goal. In this case, this cost function is minimum and is equal to 0. That's the goal. Okay? So what can you do here is to write these numbers x and y using binary representation, as we already saw yesterday. And observe that here we are considering just odd numbers, because the only one prime number that is even is 2, right? So that's the reason. So we are considering, and if 2, it's very easy to test, just check, right? So our goal is to find these values xi and yk, right? They are the solution to our problem, because with these values, we will construct the values of x and y, right? So after substituting these expressions in the Hamiltonian and quantizing this Hamiltonian, okay, you can perform all the multiplications here, right? All the terms here. Observe that y times x times y, quadratic order, but there is also a square here, so we will achieve the order of 4. But before that, it's necessary to quantize in these problems, and when I quantize this problem, I will be able to write this in the D-wave quantum computers. Okay? Let's see if you are understanding. Observe that when you have identity minus sigma z over 2, if you apply these operators on the computational state 0, what do you get here? Let's see. Sigma z. So 0, right? So this is our way of encode the classical bit 0 using this process of quantization. And if you have this situation now, sorry. What do you get? Sorry, I changed, no? Okay, it's right. What do you get now? This one you get the state 1, and this one you get the state minus 1, but with sign, okay. You now have, cat 1. Okay, here.
You define the excited state as 0, and the ground state as 1, right?
The excited state, let me see. No. Because the eigenvalue here, 0, and the eigenvalue here, 1. Every time you measure 0, every time you are talking about this state. Every time you measure 1, you are talking about the state 1. That's the way we encode this kind of information. That's clear? Okay. So after that, it's necessary to multiply all these terms. And an important question is, what is, or how many bits do you need to implement this expression and this expression? I mean, observe here that it's necessary to compute all these terms. So it's necessary to know the value of nx and ny. This is exactly the number of bits you need to write this number and this number. There is a paper in which they show that, okay, this is the right expression for the values of nx and ny. This article here. I don't know if you are familiar with the symbols, these mathematical symbols. Floor function, that means the largest odd integer not larger than w. And the ceiling function, this one, that means the smallest integer larger than or equal to w, right? So if you apply here, it's possible to have integer numbers at the end of your computation. That will be the number of bits necessary to implement the variables x and variable y. Okay? Let's take, for instance, the number 21. I want to find the prime numbers that multiplied will return 21. Okay, you already know that's 3 and 7. But how it works on the quantum computer, our first task is to write this expression here. Okay? If you apply this equation, and this equation you'll find that it's necessary 1 bit or 1 qubit to describe nx and 2 to describe ny. So that we have here x1 and y1 and y2, but observe that there are different powers until to the 4th order here. Okay, but as we're talking about binary variables, 0 and 1, we know 0 times 0 is 0, and 1 times 1 is 1, or I mean that x squared is x or y squared is y. So you can simplify these cases here, this one, this one, this one, this one, right? And our final Hamiltonian is this one. One observation here is that in the D wave, as you have some, let me say, here, observe that there are interactions that take into account at most 2 bodies. So in our final Hamiltonian, we have interaction between more than 3 bodies here. So this could be a problem. But there are different methods. I know 3 methods in which they are able to split this 3-body interaction as function of interactions involving 1 body and 2 bodies, although it's necessary to add some variables to the problem. That is important, okay? Everything has a cost to be implemented here, of course. So you use the Datani-Shaw method, okay, to write this as function of 2 variables. And at the end, or you can just try here by looking at this expression and see that if you choose xy equals 1 here, and y1 and y2 equals 1, you will substitute these values in this expression, and we will find that this equals 0. This means that, okay, this cost function, when it is equals 0, this means that we found the solution to the problem. And if you return it to the expressions of x and y, as you can see here, you'll find that the value of x is 3 and the value of y is 7. So we use this model of adiabatic computing. It's possible to implement this on the wave, but you didn't that. Just a simple example, right? But you can do, okay? And certify that this 3 times 7. Of course, the goal is to solve very hard problems with numbers and that these numbers in general have more than 100 bits. Okay, this is the real world. So at this moment, it's not possible to solve these problems using a real problem using the D-wave quantum computers. Any question?
Yeah, but how many qubits do you need to solve a problem with 128 bits?
How many bits?
How many qubits in the D-wave system
Okay.
we need to solve a real problem? A number to factorize a number with 128 bits.
I don't know actually, but of course more than 5,000 qubits they have nowadays.
Yeah, but it's huge number.
Yeah.
Qubits, perhaps.
Yeah. Yeah, it's very, very complicated problem.
Did you understand my question? I will repeat just to be on the microphone.
Okay.
How many qubits do you need to solve a real problem in D-wave system? So to factorize a number with perhaps 128 bits. So really huge number. And how many qubits?
Yeah, the answer is I don't know actually. I didn't I did do this calculation, but we know that it must be a very huge number. Okay. Yes, it's possible to compute using this expression, but I didn't do this calculation, just that. But you can do that.
128 bits would be like square root.
Yeah, exactly. Yeah, yeah, you can do this calculation.
63. He said 128 bits.
Yeah, but this n is the number, not the
Yes, this is.
representation used.
Okay.
The number with 128 bits, the number n is really, really huge.
Yes, it's 2 to the power of 128.
Yes.
So square root is 2 to the power 64 log 2, 64. So 63 for x and y is. So you.
Okay, I propose that after this talk, we're going to do this exercise, right? Okay, it's simple, but I didn't that. Maybe simple, right? But I didn't that. I don't know the numbers, just the point. Okay, this is the last application. I will show you how to use quantum computers to solve differential equations. There are different strategies, but as today we are studying adiabatic quantum computing, I decided to use this strategy. Okay, how can I use a quantum annealing to solve differential equations? Okay, this is a real application. You can find this in this reference. Okay, the goal here is to solve the heat equation in two-dimensional, right? Here we have the heat source, Q dot, and K is the thermal conductivity. This is the heat equation in the stationary regime. So time doesn't work. Here we are not worried about time. And what's the goal here is to find the values of the temperature in a two-dimensional system. That's our goal. These here are the boundary conditions, right? Let me see here. So we're going to solve this problem in a plate, in a two-dimensional plate, in a square plate with size L. There are different ways of approach this problem. one of these methods is to use in the finite element method. Okay. In this strategy, we divide the plate in several small squares, and the goal is to find the value of the temperature in each point here in this plate, right? That's our goal. So the first step is to discretize this equation. So the second order derivative here. There are different strategies, but this is one possible strategy. And at the end, when you put these two things together with Q dot here, what do you get? You get this equation. Observe that this equation is the value of the temperature in different sites. Observe here. And these sites, xy, xi here, xi plus 1, xi minus 1. Okay, so you observe that the solution for the temperature in one point here depends on the neighborhood here, right? So we decide to approach this problem and we divide this plate to implement in the D-Wave computers. We divide this in, we choose M, the division number here, 11. So we have 81 variables to find, 81 different values of temperature to find. Observe that in the boundary here, the values of the temperature, they are already defined. So that for that reason, you have to know here 9 variables, here 9 variables here, at most 81 variables. And how to implement the solution of this linear system. This is a linear system of coupled equations. To implement that, you use the same strategy. A linear system of equations is something like that, right? Here, A is the matrix that we know, B is the variable that we know, and our question is to know the value of x. A basic strategy here is to find the inverse of matrix A, something like that, but this is not the strategy we'll use here. For instance, probably who already knows the AGADL algorithm already know this is the strategy, okay? I didn't have time here to talk about the AGADL, but it's a very nice algorithm. But the reason for us to use the quantum annealing, because is that possible even take a large system of equations and get some results that have physical meaning and they are a little bit good results, right? That's the reason. So to write that Hamiltonian, we use the same strategies, okay, as we use it in the factory problem. We have a quadratic function whose ground state has eigenvalue 0, right? And our task now is to find the values xi, the values, the coefficients of this state, these components xi, and we will expand this component using floating point notation in this way. Our goal is to find the values of q, that are the bits, 0 or 1, that at the end of the computation will return the values of xi, right? C and D are constants that I define to define the interval in which I will represent my variable xy. Okay? If you encode, okay, if you replace each component of this vector x and the components of the vectors b, that are components bi, If you substitute here, what do you get? Of course, you can see that you obtain a quadratic expression, and this expression can be rewritten in this way. Quadratic term here and the linear terms here. And these coefficients that I mentioned before, they encode the problem. These coefficients A, Ki, A, Kj are the elements of the matrix A, right? And Bj are the coefficients of this vector B, C, and D I already explained. And what the meaning of this capital R and capital N? Capital N is the size of our problem, and capital R is the precision. The precision, which precision? Precision that I am writing my number xi. Okay? So, what's the goal? The goal here is to find the ground state of this Hamiltonian. This ground state of this Hamiltonian will contain the solution to our system of equations. But before we try to do that, we observe that each qubit here are the variables q. Observe that they have 2 indexes here. That's the problem, because in the D-wave quantum computers, each qubit is indexed by just 1 index. And so it's necessary to perform a previous transformation, this one. I don't know if you are interested right now, but it's possible to do that. And at the end, this Hamiltonian acquires this form. Now you are able to implement this Hamiltonian in the D-wave quantum computers. That's the goal. However, when you try to solve systems of linear equations, in the real world, we are working with matrices around more than 1 million coefficients, sometimes billion coefficients, right? So this is a problem. Of course, we are unable to do that in the D-wave quantum computers, so we decide to use small systems. As I mentioned, we have matrices 81 by 81 coefficients, but observe that each coefficient has a precision. If you have a precision, at most here in this work, we work on at most with precision equals 7 bits. So it's necessary to multiply 8 by 7 and find the number of qubits to implement. But this number of qubits, more than 500, they are logical qubits. They are not physical qubits. It's known that in the D-wave quantum computers, you have more than 5,000 qubits. But they are physical qubits. They are connected in very particular ways. So if you try to implement this algorithm with precision 7, it's necessary to have more than 500 logical qubits. That's important. And it's not easy, okay? But it was the limit. Working in a system with dimension 9, dimension 81, and precision of 7 qubits. So we decided to use a different strategy here. That is the Bloch-Gauss-Seidel method. In this method, it's possible to split the system of coupled linear equations. That was the idea. And solve each system with smaller dimension iteratively. Okay? There is an initial guess at step 0, and you start running until you arrive at step k, and there are some criteria of convergence. Okay? When you achieve a given precision, then we decide, okay, it's enough to stop now. Well, let's see what we get. The initial conditions, I mean the distribution of sources and sinks in our square plate. Observe here the color scale, right? This is a random distribution. Here we observe that the same color because it's the boundary condition. What's our goal? Our goal is to find the profile of temperature for each square of this plate. That's our goal. And we perform this calculation using the 2000 Q and advantage systems of the D-wave. Here in the vertical axis, we have this relative error. Xk is the solution to the problem. Just for the sake of comparison, we use X by direct diagonalization of the system. This is, from the practical point of view, the diagonalization of this matrix, the system of equation for this size in which we are dealing with is very simple. The problem is that we are dealing with millions and billions of equations, but for this case it's simple. Then we obtain that, okay, this is the classical solution, use the Gauss-Seidel method. It's possible to observe that the error becomes smaller as you increase the number of steps iteratively, but the quantum computer, it finds a problem here that is not possible to have the same behavior as the classical solution. Okay, to overcome this problem, what we have done was, okay, let after each step shrink the interval in which we are describing our solution, x, and this is the factor gamma. So after each step, the computer must find the solution in a smaller interval. So in this case, we found that our solution, quantum solution, can be even better than the classical one, right? So at the end, what do you get? We get this profile of temperature distribution for our example. So the final message, we obtain the solution of this, practical problem, although very small, because this is important for industry. I decided to approach this problem using coupled system of linear equations because it's important. There's a lot of softwares that are used by industries that they are based on the solution of systems of coupled linear equations. That's why I decided to do it in this way. I mean that, okay, it's a first step. Just if you have good quantum computers and with more qubits, more quality, it will be possible just to increase the system of equations and we are solving in a quantum computer. Okay? It's not clear if this approach will solve efficiently, better than the classical solutions. It's not clear for us, and there is no proof. And also the problem is that, as I mentioned, about quantum computing depends on the energy gap. And how do we get the energy gap? That's the problem. We don't know, right? So this is a heuristic method, and you can try just that. Okay, thank you. Let me just announce an opportunity. There is a master's scholarship in quantum computation in my group. I will be the supervisor at the beginning of the next year. I know that there are a few undergrad students, but if they are here and they intend to work on the field of quantum algorithms and smart measurements using classical shadows, that's a great opportunity. Okay? Thank you. Okay, before, thank you, okay. Conclusions and perspectives. Quantum computing, okay. All of you are here because we know that it's a very exciting field. I hope that this mini course is the first step for you to develop more sophisticated quantum algorithms. There are very interesting questions that are unsolvable, and I hope you enjoy. Now, thank you. Questions?
Ok. Sí, sí, se escucha. Okay.
It works?
Work. Okay, so my question was, I think I get really lost because you start by talking about adiabatic quantum computing, and you have like a target Hamiltonian and another one, and you make like a path through the both. But the examples that you show are actually you have a single Hamiltonian, and at the end you only find the ground state. So where is the adiabatic part exactly?
Okay, that's a good question. Okay. What's the importance here is to know how to build that question, the final Hamiltonian. Because these are just the information that D-Wave will need from you, just that. Because they will start from the very simple Hamiltonian, that is the sum of sigma x, sigma x, sigma x, and the scattering function you can choose as in linear interpolation, or you can invent other one. So basically, the quantum computer will do this for you. And in this example, in which we really implemented this computation in the D-Wave quantum computer, we use linear interpolation. So actually, in practice, it's necessary the initial Hamiltonian, the final Hamiltonian, and the interpolation. But what I mean here was to show you that, okay, you know that you have this final Hamiltonian, just substituting that expression, okay? Let the system evolve and measure. That's the idea. But of course, I forgot. More questions?
In adiabatic quantum computing, there are some restrictions. What are they necessary?
Why are they necessary?
Sí.
Okay. Okay, suppose that you have these energy levels, 0, 1, and 2, and so on. Suppose that the system is changed according to time. Time is here, right? And your Hamiltonian is changing according to time. So it's possible that the final Hamiltonian has this energy spectrum, right? And it's possible that this state will follow this path, and this state will follow this path. Observe that there is a crossing here. This is not good for quantum computation because your gap, delta, in this case, that is E1 minus E0, this goes to 0. So your time of computation, T, consequently, goes to infinity. That's the problem. So these constraints are very important to avoid this kind of behavior, right? In general, what you desire that you have, for instance, this one. You have a very large gap. Observe that the total time of computation is inversely proportional to the square of the gap. If you have very large gap, you have very small time of computation. This is why these constraints are very important for the quantum computer.
I have a question about logic gates. If I have two functions who are bases, I can build a logic gate.
If you have two functions?
Function and this function form a basis, I can build a logic gate with this function.
It's not clear what do you mean. Okay, I have two functions.
Yeah.
This one.
Yeah, I have two functions, and function 1, for example, is from a basis, and function 0 from a basis 2. I can relate these two functions by a constant, and with this function, who are a basis, I can build, or how I can build logic gates from a pair of function.
Okay, this is from a base. Do you mean, okay, this is a basis of a given dimension of states? I mean, suppose that this one. Different here, tipo f prime.
Or f and g, for example,
Okay.
are two different functions. Function f and g are bases and can relate it, function f with g by a constant. I can create a logic gate with this function.
Okay, but okay, if they are related by a constant,
Yeah.
I don't think so, because the states are proportional. You have just one independent vector.
One function is from, for example, beam, a laser beam with
like
angular moment. And in the other function is a function with angular moment, but in another coordinates. And I can I can find a way for related these two beams by a constant. I can prove these two functions are bases, and I want to build a logic gates with these two beams for encoding quantum information.
Okay, let me see if I understand. If you have, for instance, the angular momentum of light in the Laguerre-Gauss basis, and you can move to another basis.
Yeah.
The question is there a quantum gate that performs this transformation? That's the question.
Yeah, I am working with a Laguerre-Gauss beam, and by other hand, I'm working with a perfect vortex beam. I can prove a perfect vortex beam from a base. Then I want now create a logic gate with these two functions. But I don't know who is the process for generate a logic gate for made a process for encoding quantum information.
Okay, but the answer is yes. Suppose that you have to map your Laguerre-Gauss states in the computational basis. And your other base, you map to plus-minus bases. Observe that these two states are connected by a unitary transformation, and chain of base is a rotation. It can be a unitary transformation, so it's possible. But how to do that? It's possible you put one base states inside a matrix and the other base states here. Here, and try to find the coefficients here. And you know that it must be unitary, so there are some constraints between this coefficient. Then you are able to find the transformation.
I understand. Yeah? Thank you very much.
Okay. There is another question behind you.
Hi, actually I have two questions, but the first one is related to something that Enrique Solano the first day told us about a shortcut to do adiabaticity. What is the counter-diabatic driving? I don't know if you can elaborate a little bit about that, if you know it, or I don't know if he's here. But.
Yeah, I can talk a little bit.
Okay.
Okay. The idea of adiabatic quantum computation is that you start in this state. This is the ground state at the initial time, ground state. And you go to the ground state at the final time. Okay? Observe that this path was performed under the constraint of adiabaticity. But suppose that you want to arrive here, removing this constraint. What can you do here? You can use shortcut to adiabaticity. That is a different strategy. So This work, this proposal was made by Michael Berry in 2009. The idea of Berry was the following. Okay, I know that I have an evolution operator that describes the adiabatic evolution. How can I build a Hamiltonian by add another term to the previous Hamiltonian and find the same eigenstate at the end of the computation? Let me try to. Okay, suppose that your unitary operator is something like that. I believe there is a phase here. Here. The idea is, okay, we know the evolution is this one. This evolution, observe that if you start, like here, 0 is time t, observe that this kind of evolution operator just move the same state with the same label, right? So this is the kind of evolution operator for adiabatic evolution, because there is no transition. So what can you do? You must replace this unitary operator in the Schrödinger equation. But what are you doing now? You are asking, who is this Hamiltonian that implements this evolution, right? That's the idea. But what do you do first? First, to your adiabatic system, you describe where do you want to go, right? I want to go there, and I know this one, so I perform this calculation, and I find this Hamiltonian. This Hamiltonian says, okay, there is no constraint, no more, but with this Hamiltonian, I'm able to implement this time-dependent evolution in a very fast way. What the price you pay? You will add some terms in the adiabatic Hamiltonian, and in general, to implement that, it's necessary to know the eigenvectors of the Hamiltonian. That's a problem, because as I mentioned earlier, okay, if you already know the eigenvectors, you already know the full solution of the problem. But there are different strategies in which it's possible to approximate these corrections. Very recently, they found that, and that this works. That's the reason for this works. Okay? It's clear?
Yes, for me it's clear. The last question is just a curiosity. I want to know, for example, in this case, when you explain the adiabaticity, the levels that you're explaining is actually the eigenlevels or the eigenenergies of the system. I don't know if there are some work related to, instead of working with the eigenenergies, for example, to apply a periodic driving in the system in order to work instead of the eigenlevel, the quasi-layers that form part of the Floquet formalism. Maybe you have more degree of freedom in order to avoid that gap, but I don't know if there is some work related to that.
Okay, I am not specialist on this subject, but I was talking to someone, I don't know who, you, both of you. Maybe your work may be related to that question, right? I don't know if you work exactly with Floquet, this kind of post, but you can talk later, okay? But
actually,
it's
yesterday was talking about.
Really? Okay, so there are different strategies. I already worked in the past using dynamical invariants. That's a different approach. It's not adiabatic. Also, the idea of working this kind of dynamical invariants that you are able to remove the adiabatic condition. But of course, there are some penalties because you are working on the excited states. When you are working on the excited states, the coherency is stronger. Okay, this is a problem, possible problem, right? More questions? One here.
Yeah, two questions. The first one, which is the short one, what's the runtime of the last result that you showed us?
Runtime? Okay, the question is?
Oh, it was the last part. But the runtime in the D-Wave machine, how much did it take to obtain the results?
Could you remove your mask, please? I don't understand.
Just the runtime in the D-Wave machine.
Okay.
How long it took to retrieve the results?
Okay. The runtime in the D-Wave machine is about, I'm a bit confused now, but I guess it's millisecond or microsecond. Someone record, no, okay. I guess in the D-Wave machine we spent, to implement the initial Hamiltonian to the final one, we spend milliseconds or microseconds. I guess it's millisecond. I'm not sure. But the problem that there are several steps that are involved. For instance, the time to prepare an initial state, time to prepare for a measurement, entendeu? Okay, did you get, okay. I mean, there are different times that at the end they are bigger than this time of just starting from the initial Hamiltonian and going to the final Hamiltonian. That's the, but the important thing that this time are a bit, I mean, constant. And if you take very large problems, real problems, at the end, this time between the initial and final Hamiltonians, that will be the larger time, right? But at this moment, it's not the case.
And the second one is if you can elaborate a bit on the universality of the adiabatic quantum computation.
Okay.
It's not completely clear for me how you can perform any task in that model.
Okay. This paper is not much simple to follow. It has hard mathematics, okay? But this was proved by Seth Floyd and other authors. One possibility is to think about the discretization of the adiabatic evolution that is continuous. You can think that this evolution occurs in steps of time, and each step can be written as a quantum gate. And by counting this, you can show the equivalence between these two methods. This is a possible strategy. Okay, I don't know. I am not saying that it is easy, but it's necessary to go deep in the paper. And
but wouldn't it be like somehow simulating the adiabatic evolution in a
digitalized
digital?
Yeah, something like the variational quantum algorithms, as Professor Askeri will talk to us tomorrow, no? On Friday? Next week. So we'll have the opportunity to understand this process, okay? You can digitalize the adiabatic continuous evolution. It's quite similar.
I'm not sure if I understood. You're saying about digitalizing the adiabatic evolution, but about the equivalence between...
yeah, it's possible. I mean, adiabatic evolution, to perform this kind of evolution, it's necessary a Hamiltonian, a many-body Hamiltonian. But observe that the evolution of this kind of system, it's necessary in order to written as function of 1 and 2 qubits, it's necessary to break all the parts, and in order to get the gates. That's the idea. So this is the digitalization process.
And can you do it like the other way? Let's say you have a digital process, and then you want to do it, but from the other side. It's because it's like one way, but
okay.
Is it possible to be completely equivalent?
Okay, let me think a minute. Yeah, Yeah, it's possible, but I'm not sure if there is only one way. Maybe you can find more than one solution to the same circuit. I think that's the problem. Okay?
Thank you.
Okay, I'm sorry, but you have to stop here.
Okay.
Let's thanks again, Professor Eduardo.